Hi, this particular video is going to be on the assembly of my version of Julian Eyelet's PWM5 charge controller. This is a through-hole version of a much smaller one that I have been selling as a kit for some time. That in itself was also I won't say a rip-off of Julian's, because he gave me permission to make them. It was a direct copy of Julian Eyelet's. I just tweaked the circuit layout to suit my own needs. This is I call it the Pico. It's 15 by 25 millimeters, all surface mount, with the exception of the TO220 MOSFET, which I actually lay over the surface mount PIC 12F683. But this video isn't about this baby, it's about this one. This is in response to a few requests I've had where people have been unable to solder surface mount. So I have been thinking about making a through-hole version for some time, and then before I actually managed to knock the board up, Julian Eyelet also decided to start manufacturing. Well, not manufacturing, he's just making a few for his own personal use, but he's decided to do through hole because he's not keen on surface mount himself. So bizarrely enough, it's just a bit of a coincidence that we've both sort of come up with the same thing at the same time. But this is my version of his original PWM5 design. It's a 35 by 35 millimeter surface board. The track layout is double-sided, but all the components just go on the one side because that's kind of like the standard form for a through-hole board. I've compressed it as small as I can, and in fact I've actually decided to stand the resistors vertically on the board, partly because I actually quite think they look quite interesting stood up. It kind of reminds me of like those old circuit boards that used to come from cheap products when they were made in the Far East many years ago. Normally Hong Kong, kind of like transistor radios and stuff. All the resistors were vertical, and I used to repair that sort of stuff, so I kind of got a bit of a fondness for it. So I designed this to mimic that in some way. This uses just conventional through-hole components, exactly the same sort of thing that Julian Eyelet has made when he made his as a production model. I've not actually changed the tool. I've run pretty much with his design. On the high power tracks, I've double-sided it, stitched it with wires just to reduce any losses through the board, because it can handle 6 amps. So you've got a 6 amp track running here. It looks very small, but actually it's on the flip side as well, so it's on both sides of the board. That's the same for all power tracks. All the rest of it is just standard tracks routing the components together that don't require heavy loads, and that's it. It's quite a nice design. I've done it in this fetching blue, which I thought was rather nice. Bit of a change from the norm. So I shall start assembling the thing now. Normally when I assemble these boards, I tend to do the flattest components first. So in this instance it'll be the diodes. I'm not going to bore you with all of the intricate soldering and stuff. That's been done hundreds of times by loads and loads of people. So I should just do little snippets of the build as it progresses. It shouldn't take me much more than about 20 minutes to put together, so we'll see how we go. Right, that's all the diodes put through the board. I've not soldered it yet. I've got a porcupine out the back with all the pins, so I shall just get those soldered now. Right, that's all the diodes soldered in. This thing won't focus on that too. There you go, they're all soldered in. ready to move on to the next stage, which in this instance I think I'll probably put in the transistors and the voltage regulator. Actually, what I'm going to do is I'll put the voltage regulator in first and its support components, and then I'm going to test that it's producing 5 volts at pin 1 of the IC, which is a good place to start. Save any unfortunate accidents with a programmed PIC683. Right, the silk screen on these has been done so that the device it's easy to line the device up. With the exception of the LED, it's very difficult to see on the LED which way around the silk screen is, because the flat just isn't really very clear. And in fact, on my revision 2 board, yes, this is number 3, I accidentally put the silk screen around the wrong way, which is a bit annoying. So there's a bit of a trick for young players there. Make sure that you have the components around the right way before sending the boards off for manufacture. Right, with this kit I've supplied tantalum caps. Now, normally capacitors are marked on their cathode, on the negative, but tantalums bizarrely are marked on the positive, which is a bit of a confusing one, especially since the silk screen is marked like a conventional electrolytic with the marker on the cathode. So it's important just to remember that when you're installing tantalums. If you put them around the wrong way, they kind of go up in flames. They're quite volatile like that. So yes, they definitely need soldering the correct way round. Right, I've got all the voltage regulator components in for the 5 volt power supply for the 12F683. It consists of a diode, reverse protection diode, reverse polarity protection diode, which is linked straight to the positive rail, which is this one here, this particular rail here. It links through and winds its way up to here, then shoots across onto this tantalum, through this tantalum, and then to the voltage regulator. The voltage regulator grounds straight to the ground rail on a link through, which then continues through the centre pin, through this ceramic capacitor to pin 8, which is the ground. The 5 volt regulator output is on this side, so that goes through the other side of the ceramic capacitor to pin 1. So in a second I'm going to get my DMM out. I'm going to apply 12 volts to this point here, the battery positive and the battery negative, and I'm going to put the meter on the pin 1 and pin 8 just to make sure I get 5 volts. Right, excuse the sea of wires. Not quite in the middle here, are we? Right, now I've got my bench power supply set to 12 volts. That comes through here. So just put the leads quickly onto there. You'll see the meter showed 12 volts or thereabouts. 11.99, that's close enough. So what we're looking for is 5 volts on pins 1 and 8 of the IC. And we're showing 4.97, 4.98. I do find these LP2950 voltage regulators are normally a little fraction low. I'd like to see them bang on 5 volts because that actually helps the chip calculate the actual battery voltage. But because these run a little bit low by a couple of hundredths of a volt, you find that the voltage analysis is out by a percent or so. So when the battery, say, is supposed to be float charging at 13.5, quite often it'll float charge at 13.7, sometimes 13.8. It doesn't actually matter to a sealed lead acid battery or an open battery. It's a couple of tenths of a volt. A couple of hundredths of a volt doesn't make any difference, but it's not quite as accurate as it should be. Julian Eilert is looking to make a software tweak which will correct this, but at the minute it'll just have to stay as it is. I'm quite happy to accept a charge voltage of 13.7 or 13.8. Certainly none of the batteries that I've had these run for on about 12 months, they don't show any sign of damage. In fact, one of my batteries is now 8 years old, and I tested it 3 days ago. It's just a small 7 ampere SLA, and the last time I tested it, it was 6.9 amp hours, and I tested it, that was 8 years ago, and I tested it just 2 days ago, and it was showing 5.84 amp hours. So it's lost about an amp hour in the last 6 years or 7 years, I think. So and 12 months of that it's been on one of these, so they're obviously not going to damage the battery in any way, shape or form. Right, now that the chip's power supply has been checked, the voltage regulator is outputting approximately 5 volts, give or take a few hundredths. It's time to continue installing the rest of the components. I'm going to put the transistors in next, and then the tantalum, the transorb, which is a transient suppressor, and I'll put the LED and then the resistors on this side, and then I'll finish off with the PIC micro and the MOSFET, which goes in here. But let's get the transistors in now. I just thought I'd mention that when I'm soldering, I tend to use extensive use of this stuff, blue tack. Quite a lot of hobbyist circuit board builders use this stuff. It's actually amazing for all sorts of weird and wonderful things that it wasn't ever designed for. Of course, it was designed for sticking bits of paper to walls and windows and things. But actually, I find it really good at both holding a component in the right place for soldering, like I'm just about to do Q1 here, and then you can just stick the whole thing down, so you can solder in at relative ease. Let me just see if I can get this one soldered in on camera. Right, there we go, that's soldered in nicely. Just trim the porcupine off the bottom and I'll do the next one. Right, I've jumped ahead a little bit here. I've put all the transistors in, put the LED in, the capacitor on this side, which is part of the voltage divider. I'm just about to put the transorb in. Just one thing to note on these is the transorb is non-directional. It's got a double diode symbol on the silk screen, and in fact it is a kind of a diode in both directions, but it's open until the voltage exceeds 36 volts on this. So I've pre-bent the pins, it just fits in there like that, and then I shall solder that one up as well. Right, the next job to put in is the resistors. There are only a few values on this. There's actually 3, all the same value. These are 220Ks. They are 4, 5 and 6. R4, 5 and 6. You've got a couple of 1% resistors, which are these two. I believe the blue one is 20K, and this light, the green coloured one, is 82K. It says so on the bands, but I find that these dark coloured enamels are so difficult to actually read. It's just quicker and easier. I actually know what the colours are because I just happen to see them and recognise them just from sight. But actually reading the colour bands is so impossible, especially with these 5-band on these little 1/8 watts. It's easier just to measure the resistance on a DMM. I suspect most people do that these days. I don't even know how many people actually remember the resistor code because we're all surface mount these days. Yeah, just measure them on a DMM and then just make sure they go in the correct locations on the board. Alright, like I said at the beginning, I've sized the spacings on the board here for mounting vertically. So I mean, it's really easy to mount vertically. You just kind of like bend them over and then tweak them till they look nice, and you just stick them in the board. I remember doing this when I used to repair those cheap radios many years ago. I quite like them. I think they look quite I don't know, old-fashioned in a weird kind of way. I tend to shape the leads so that they look... you can actually buy resistors pre-formed like this, so all in a band, ready just to install. But they're very they're soft copper, or probably iron these days. But that's what I do for the resistors, and that's how the board has been sized. Right, that's all of the support components in. There's only just 2 remaining components, which is the PIC 12F683 and the MOSFET, which is going to go here. And that's it done then. Oh, actually, I tell a lie. I've got 2 more capacitors to put in. Let's just do those now. Right, well, that's now all the support components in place. I'll put the MOSFET in next. Now the MOSFET is very close to the transorb in the way the tab sits. You'll see when the MOSFET fits on the board, to get it as compact as possible, you have to bend the legs right flat to the body. It doesn't affect the MOSFET too much, not at the current we're running. It's only running at 6 amps. It'll take a bit more than 6 amps without getting too hot. But when the MOSFET is mounted, you'll notice that it is very close to the tab here. Now actually, the tab and this leg of the transorb are in fact the same. They're the same. You could solder them together. It wouldn't make any difference. But I'm not a fan of close electrical components like that. So what I've done is I've just got some little silicone boots which slide over the end, and then this will just sit there and it'll cover it. It'll just protect it from any possible shorts. Now it can't short because it's the same potential, but it just makes me feel better about the whole thing. So that's what will be included in the kits, with this little rubber condom, they call it, a silicone condom, and it'll just protect the tab of the IC from the same potential transorb. Right, it's time to fit the MOSFET. On this particular board, the MOSFET is folded right at the body, so it's easy enough just to do that on the work surface. Just sling it to about 90 degrees like that. So that's at 90 degrees, and it can just go straight into the board. You will notice that the tab will touch the transorb, the TVS, transient suppressor, and it's quite close to the other components as well. So like I said, I think I already mentioned, I supply a silicone condom, which is bizarrely what it's called, which helps insulate it. This just needs cutting down very slightly to about the same length, otherwise it overhangs and looks a bit strange. I find that these you can just nip the bottom out at this point here, just that little area there, and then slide it over and then solder the device into place, and as long as you apply some pressure it'll hold it in place. So I shall go and do that now. Right, the insulating condom cover is always makes me laugh when I say that word. It's cut, so now it can just slide straight over the device and solder it to place. And once, if you press it down and solder it, it actually sticks quite firmly. I shall just do that now. Right, I'll put a lump of blue tack on the back, so just push it down onto my board, get the soldering iron out, and I shall just solder that up. Now the tracks are quite thick, like I said, they're double-sided, so they do take a bit of warming up before they'll flow solder, except for that one, which will flow solder very easily. I've used plated through-hole wires, so the solder wicks right through. That's it. And that's it, the job completed. All it needs now is just to have the legs trimmed, and it's ready to fit the PIC 12F683 to the board. Alright, the PIC comes in, it's pre-programmed, so it just needs installing. Obviously, with all chips you need to make sure that it's installed the correct way around. Pin 1 is on the left when you've got the little half moon cutout on the end, so you just copy the half moon cutout on the board, which is replicated just there. So, and pin 1 will be on the left here, which is just there. Right, so it's just a case of carefully remove the PIC from the ESD phone, make sure it's orientated the correct way around, drop it in, make sure you don't bend any pins in the process. Another lump of blue tack, stick it on there, solder the pins in. Right, the PIC's been soldered in. The pins don't need chopping off on the PIC, they only come through a fraction more than all the rest, so they really don't need cutting down. And at this point the board is complete. Everything is installed where it should be, the MOSFET is in, it's got its cover in place, so all that's left to do now is to test it. And fingers crossed, if I've soldered all the components into the correct places, it should work without any trouble at all. So let's give it a go. I'm just going to run it off my bench power supply, which is an easy way of adjusting the battery voltage without actually having to do anything complicated. There's no sun, it's about 10 o'clock at night, so I can't borrow my solar panel power, so all I've got to do is just connect up my bench power supply to the battery leads on here. This one is the positive, it's on the MOSFET side. Connect the other end to my bench power supply, and we should see it. Bench power supply set at 12 volts, so we should see it produce some voltage. I should just set the current down to 100 milliamps just for that's bizarre, isn't it? My bench power supply is, one moment. Alright, sorry about that. My bench power supply decided it was going to short the pins out on a pair of tweezers. Rather confused me because it was showing full current and there was nothing connected. So, bench power supply is set at 12 volts. So let's just connect it up and see what happens. Right, it's booted. The 2-second blue light means the processor has boosted, and now it should enter voltage display mode, which is a series of flashes. And that just showed 2 flashes, I think. Then the camera doesn't always pick up all the flashes. Yeah, so it's showing 2 flashes. Now 2 flashes actually means 12 volts. It assumes that the 10 integer is already there because it doesn't display any less than 11 volts. So all you have to do is add 10 to whatever you see. So 2 flashes is 12 volts. And if I increase the voltage to, say, 12.5 volts, oh, I've gone a bit too far, 13 volts, interestingly enough, it's actually showing modulating. I don't know why it's modulating. Oh, I've got power supply problems today. I don't know what's going on with my power supply. Right, try again. There's the boot. My power supply seems to have gone very inaccurate on its display. Right, I've set the power supply to 12.5. Let's get a DMM into the picture and see how accurate the... Let's just move that. Sorry, I have junk everywhere. Let's put that on that side. You can read that. See if I can't get this into shot as well. Right. So it's showing 12.49 volts. And how many flashes? 1, 2, 3, or 4 was that? 1, 2, 3, 4. So it's showing approximately 0.1 volts under the actual voltage. I wouldn't say this unity meter is particularly accurate. My bench supply is also showing 12.5. Let's just nip it up to 13 volts. Now this seems to be modulating too early. It's modulating at 12.8 volts. Now I'm wondering if I've put the resistors around the wrong way, which is a bit strange. Let me just investigate that.